And so now we will have Dorette Pronk with Doubly, Lux, Colimits of double categories. Dorette, take the stage whenever you feel like.
Okay, thank you. Thank you to the organizers for organizing this both local and global conference. And I am grateful to be able to be part of it. And thanks to the scientific committee for letting me speak. And so I want to continue the story about two categories that was started earlier this morning for me at least. And we're going to look now at what we call double categories. It's still a two-dimensional version of category theory. And I'm hoping to introduce a new version of colimits for these structures. And this is joint work with Margie Abaye and Martin Tilt, who was willing to even help me give the talk. Can I go to the next slide? Thank you. So double categories, actually the way I want to see them today is a little bit more symmetric than what the definition gives you. So the definition I'm going to quickly give is that of an internal category in CAT. So C0 and C1 here are categories. And of course, there's a bit more to the diagram than the source and the target map, but I wanted to keep it simple. So a double category has objects that are the objects of C0. It has what we call vertical arrows, just because we have two kinds of arrows, we'll call one vertical, the other one horizontal. Vertical arrows will be the arrows of C0, and with then just their own structure for domain and codomain, and we all denote them with the dots. We have also horizontal arrows, those are the arrows of C1, and their source and target are given by the S and the T functor in the diagram. And then we have double cells that have both horizontal and vertical domains and codomains and can be composed horizontally and vertically. You don't need to know too much about the details here. Thank you. So no, keep going. That's good. So the any two category can be viewed as a double category. And there's kind of three canonical ways to do that. There's the quintet construction that Erisman already introduced in his work, and where both the horizontal and the vertical arrows are the arrows of the original two category. Then there's a horizontal version where all the arrows from the original two category are in the horizontal direction, but vertically we only use identities. And there's a vertical version that goes dual. Go to the next one. Okay, so the double category, the category of double categories is in some sense not as nice as the category of two categories, because the category of two categories can be viewed as a two category itself, or actually a three category, but in any case, it has the two category structure. The category of double categories does not have the structure of a double category, but it does have other structures. So let's look at it, what it does have. Objects are double categories, obviously. Arrows are double functors that are preserving all the structure I just told you about. And then we have two cells, but they come in two flavors. So there's two kinds of two cells. There are vertical transformations, which are like Nick's Oplax transformations, or well, Lax or Oplax is not as clear here because we don't really give a direction to our double cells, but they are like those Lax or Oplax transformations, but with vertical components, and then the horizontal transformations, which are the same way, but then with horizontal components. And then there are modifications. So next slide. So we see that double cat itself is not a double category because we have only one type of arrows, but we have two types of two cells. So it's actually enriched in double category. So every HOM is a double category. And if you restrict yourself to either the vertical transformations or the horizontal transformations, then you end up with a two category that we have indicated by the little v and the little h there. And Lax limits in the past, so Lax limits are defined in terms of Lax transformations, or so they can be done in either the horizontal or the vertical direction. Next slide. But we would like to have limits that have some kind of laxity in both directions. And so the first question is then, okay, so what is the diagram for which you take the limits? So we need to talk about indexing functors, and we would like to have an indexing functor that has a domain, a double category D. So what can we do? We have to send the object of D to double categories. We have to send both the horizontal and the vertical arrows to double functors. There's nothing else to send them to. And then for two cells, we actually get a choice. We can either send them to horizontal or vertical two cells. And we have opted today to take vertical. In this story, because everything is strict today, it's really, you can take my whole talk and switch vertical and horizontal and it won't make a difference. So it's, but of course, do all the switches in that case. So we're going to do vertical two cells, and the zone indexing functor is actually now a double functor from D into the quintets on the two category double cat V. That's what we have basically done by what I just told you. And rather than writing that mouthful every time, we'll talk about vertical double functors and from D to double cat, and that's it's an abbreviation for what I just said. And we'll also sometimes call those vertical index functors. So now the question might be, have you just lost your horizontal transformations and your modifications? Have you lost the ability to distinguish between horizontal and vertical arrows in the indexing category? So is this actually doing anything? And the answer is yes, you have not lost this. And we will recover this in the notion of a doubly lax transformation. So let me give a quick overview for how we're going to define them, and then I will define them. And so we're going to take the same approach that Benabou took when he introduced transformations for bicategories. And he did this in terms of cylinders. So we're going to introduce a cylinder double category. Now, in principle, there's two versions for that one. We'll use the vertical one today. So we'll call these sometimes vertical cylinders on double cat. So the cylinder double category can be defined for any category that is enriched in double categories. So in particular for double cat. And it comes then with two vertical functors into double cat. So remember, those are functors into Q double cat V, but I'm not going to say that anymore. And now between such vertical double functors, between vertical double functors, we can then define a doubly lax transformation by giving a double functor from D into the cylinder double category on double cat, such that D naught, so the top of the cylinder, will D naught after alpha will give me F, and D1 after alpha will give me G. So it's the same setup as we had for bicategories. And I'm now going to spell it out. So first, what is this cylinder double category? The objects are going to be the double functors, and we will write them as a vertical arrow with the label of the functor. The vertical arrows, so remember in the cylinder category, normally the arrows were squares, commuting squares, or squares commuting up to a two cell actually. So in this case, we will have squares that are commuting up to a vertical transformation. So for vertical arrows. So a vertical arrow from F to F bar is a square as given there in the middle. And a horizontal arrow is another one of those squares, but now with a horizontal transformation. So the vertical transformations in a square give me the vertical arrows. The horizontal transformations give me the horizontal arrows. And of course, we need now the cylinders. So those are the double cells in the cylinder category. And if you look at that square on the top, if we just look at the frame of the arrows around it, you have the information there for what you could think of actually perhaps more of a cube than a cylinder, but where we have all the sides of the cube already. And then we just need the top and the bottom still to complete that. And the top will be the alpha, the beta will be the bottom. And so they are going to be vertical cells. So we have for the sides, we have horizontal and vertical cells. For the top and the bottom, we have these vertical cells. And then we have a modification that fits into the whole picture. When you work it out, you can see that the vertical transformations can compose to make vertical transformations on the sides there and the horizontal transformations. So basically, when you want to go from the cube to that diagram on the left, you need to do a bit of a turn by 90 degrees to get the horizontal transformations in the right place. Thank you. So now there are the vertical double functors giving you the top and the bottom of a cylinder. And if we're looking at two vertical double functors F and G from D into double cat, a transformation is given by a double functor from D into the cylinder category, as we said. I'm gonna, in the next slides, explain what the details are. So let's look a bit more carefully at what that means then. So for each object, I'm going to have a double function. So if you have a theta from F to G, for each object, we will have one of those vertical arrows here, theta A primed, and so on. And then for each horizontal arrow, we will have a horizontal transformation to fill the square on the left back and the right front with F for F and for F primed. And we have vertical transformations for the left front and the right back with U and V. And the theta alpha is then this modification inside. So for a double cell goes to a modification that will fill that cylinder. And the top of the cylinder will be F alpha, the bottom of the cylinder will be G alpha. So we see that this cylinder, thank you, this cylinder has the both horizontal and vertical transformations as part of its structure. So we haven't lost them. They are showing up in the transformations. So continue on. Okay, so we see then that the doubly lax transformations between vertical double functors are represented by double functors. Double functors have, of course, horizontal and vertical transformations and modifications coming with them. So we see that we can give the HOM from F to G the structure of a double category. It's a sub-double category of the one from going from D to the cylinder double category. Thank you. So we can now define doubly lax cocones as vertical, as doubly lax transformations from the given vertical double functor F into the diagonal on a given double category E. And because the transformations between two vertical double functors form a double category, we can say then that there is a double category of cones under F with vertex E. And if I now wonder whether a particular lax cocone would be the doubly lax colimit, I can use the standard way of defining the universal property that if I take a functor from my proposed colimit to another double category E, I can compose that functor with the cocone to get a new cone with E as its vertex. And we require, now we see that this structure, this map has a double category as domain and codomain, and we will ask for that be an isomorphism of double categories. And the nice result that we are excited about is that a doubly lax colimit can be obtained by a double Groton deconstruction. So that's the next slide. So if we have a vertical double functor, the double category of elements is going to be defined as follows. Objects are pairs of objects, just like we do it in the classical Groton deconstruction of an object in the indexing category together with an object in the image of that particular object. So Vertical arrows are also defined in typical way for a growth and deconstruction as these pairs, and horizontal arrows similarly. So there's nothing new on this slide yet, but the next slide shows how the double cells go. So for double cells, we also have to work, of course, with the pairs again of a double cell in the indexing category together with the double cell that we are going to make in FD primed. And how do we kind of take the same approach as you would have taken for if you were doing this for a 2 category, except that in this case, in order to close up in the top left-hand corner, we need to use a component of F alpha sub X. So here's where we use the fact that F alpha is a vertical transformation so that we have that component there. And if you had done what I told you could do is change vertical and horizontal, that F alpha X would have ended up on the horizontal part. So you would have gotten a flip of this type of diagram. Okay, so I'm not going to give you the proof that this is the colimit, but I can sketch at least the idea. In the classical case, this is depending on the fact that we can factor every horizontal arrow as a Cartesian arrow and then what we sometimes call a vertical arrow or arrow in the fiber when we think in terms of vibrations. So we can do the same thing, of course, with our horizontal and vertical arrows here. And our double cells factor very nicely too. Here is the diagram for that. And it's this factorization that helps us to prove that we indeed have the isomorphism required to get the colimit. Let's continue on with the next slide. So there is a doubly lax co-cone, which I just have sketched out, with the required universal property that we indeed get the isomorphism of double categories. Furthermore, we can also extend this growth and deconstruction to a whole functor of double cat enriched categories and obtain the more general notion that we know from the classical case as well, that we get locally isomorphisms of double categories between the double category of doubly lax transformations with the structure that is there, and on the other hand, the slice category over D of double functors between the growth and deconstructions over D and then transformations and so on. So there's an isomorphism of double categories there as well. And on the one hand, actually, when we proved the second result, we used the first one to extend it. But on the other hand, once you have the second result, you can also see that the first result is a quick consequence of it. As applications, as we have seen in the past, once you understand colimits of double categories or limits of double categories, they help us to understand limits and colimits in 2 categories better. And that is the case here as well. So we can actually view a lot of several of the classical constructions now as special cases of this one. And that's not surprising. But what's nice about it is that we get a universal property here that then gives us a universal property for the classical cases. So for instance, if we take an ordinary 2 functor from a 2 category into 2 cat and then apply V to it, then it turns out that that would give me with another, and then that would give me almost a vertical structure. And then we need to do one more V so that I have actually a vertical, so that I have actually double category as my indexing category there. Then it turns out that if I do this there, if I do our construction, we get the vertical embedding of the classical 2 category growth and deconstruction as given by Barkovich and Buckley. But this V is an isomorphism of 3 categories between 2 cat and its image in double cat V. And so we see that we can prove, this is a different way of proving that the classical 2 categorical growth and deconstruction is actually a lax tricolimit in TOCAD. Another one that we just noticed was nice. If you apply a flip in the process so that we have both F and F op hanging out in the end in the construction, then as described here, we end up with the read products introduced by David Jasmeyers last year at the Applied Category Theory Conference. And so this provides us then with a universal property for his construction. We actually started this project because we wanted to construct a finer homotopy invariant for G spaces. So we have a fixed topological group G and acting on spaces. And we were wondering whether there would be a double categorical version of the Tom Dieck fundamental groupoid. Tom Dieck fundamental groupoid is really an lax colimit of fundamental groupoids over the orbit category of a topological group. And the way it works is that it uses paths in the different, it uses the fundamental groupoids for the different fixed point sets. And they, so we were like, okay, can we do a double uplax colimit? And what we added in the vertical direction is paths in the groups. And that actually gives us a finer invariant. We're still working out some of the details, but we have already some spaces that cannot be told apart by the Tom Dieck fundamental groupoid, but can be told apart by this one. Of course, the next question to ask is, can you do this in a pseudo functors? And the right notion is that of a double pseudo indexing functor. The double pseudo is defined by Mike Schulman, and we have done the construction. We're still working on proving the universal properties and stuff like that, because there's a bit more work to be done there. It gets a lot more technical as soon as you put these extra cells in. And but the goal is then to extend the results further and then also obtain a notion of vibration for double categories that would fit with the images that we would get under the Grothendieck deconstruction. So we would like to be able to characterize these functors into D that are coming from the Grothendieck deconstructions, and we have also a goal there, but we have a conjecture, but we're still working on the details there. Thank you.
Thank you very much, Dorette. And now we have time for questions. So if someone has a question. Do we have questions live? Oh, yes, we have one question.
Okay, thank you for this very interesting talk. My question was, in the same way that you recover pseudo colimit of category as a localization of the lax colimit, do you have some notion of double localization so that you could recover a double pseudo colimit from the Grothendieck construction you had at some Cartesian cell? Or?
Well, thank you for the question. This is actually one of the things that has been on my mind, but no, we haven't done that yet. And so, and I certainly would welcome collaboration on any of that if people are interested. Although Martin might be interested in doing that as well. Yeah, so I have some ideas. There are some that you have to be quite careful in setting up the right formalism to do double categorical localization. just the different classes on two directions. Although I think that this one might work here because we are kind of focusing in one direction. So there's a better chance of, here's at least there's a clear guidance by this, given by the construction to do it. Because I remember a number of years ago, just trying it in complete generality and realizing, okay, I'm swimming in an ocean, this is too big. And so, so we haven't done it yet in any case, but I would be very interested.
Okay. So if I may ask a question myself, so if I may ask a question myself.
Yes.
So you said that the Grothendieck construction that we all know about, if I understand, is a LUX3 colimit.
Yeah.
And this is something personally I was not expecting. Was it like expectable? Did you expect it? And do you have some comments on it?
Well, so it's kind of funny because even though I'm a category theorist, I actually learned mostly about the Grothendieck construction from the homotopy theorists a long time ago, just because they were there sooner than the category theorists in my life. And so I always thought about the Grothendieck construction as a colimit, until somebody told me, no, it's a vibration. And so, of course, it's kind of both. But, well, actually, no. So it's I think I should say, a priori, you probably should think of it as a vibration, because that's usually what you get first. And then you can check at the colimits, whether the colimit works. I mean, I'm actually working on another project where we still are asking whether it's a colimit. So, but yeah, so in my mind, I wasn't too surprised. The question is always which colimit. Well, I'm expecting generally a LUX or OP-LUX colimit, depending on what direction your OP-LUX goes. And then indeed, in order to make it a pseudo colimit, you would have to do some kind of localization. I mean, this was given by Grothendieck in the first place when he introduced it. So I'm always hoping, at the very least, it would be the first thing I would want to try. I realized that that proving it can be quite tricky, and so it's nice when you do this double categorical version, and it can give you a bunch of the two categorical versions for free. Just because there are always so many little details to be checked at this level.
Thanks for the answer. And if there are no more questions, we thank the speaker one last time.
And I want to thank my assistants, because without your help, I couldn't have done this one.
No problem, no problem. And we move to our next speaker now.